Grab one end of a rope and drag a box across the floor. We usually say the tension is the same everywhere in that rope. That's true, but only if the rope is massless. Give the rope real mass and the tension quietly changes from one end to the other. Today we'll see exactly why and derive how the tension varies along a heavy rope. Start with the simple case. A very light rope, so light we treat its mass as 0. Call the rope object 2 and the block object 1. The rope attaches to the block at point B and someone pulls the far end at point A. Set up axis. J hat points up, away from the surface, and I hat points along the pull, in the positive x direction. The applied pull is the force F sub A2. Apply Newton's second law to the rope alone. Two horizontal forces act on it, the pull F sub A2 to the right and the block pulling back F sub 12 to the left. So F sub A2 minus F sub 12 equals m sub 2 times the acceleration. Here's the trick. If the rope's mass is negligible, that right-hand side is 0, no matter what the acceleration is. The same holds if the system moves at constant speed. Either way, F sub A2 equals F sub 12. Now the block. Along the direction of motion, the rope pulls it forward with force F sub 21, and the friction F pulls it back. When the block isn't accelerating, F sub 21 minus F equals 0, so F sub 21 equals F. Newton's third law links the two objects. The force of the block on the rope, F sub 12, equals the force of the rope on the block, F sub 21. Chain them together. F sub A2 equals F sub 12 equals F sub 21 equals F. The pull you apply is handed straight through the rope to the block, undiminished, and here it also equals the friction. So far we've only talked about the force at the ends of the rope. What about the force in the middle? Here's how we define tension at any interior point. Imagine slicing the rope with an imaginary cut at a point P, a distance x sub p from the block. That cut splits the rope into a left piece, L, and the right piece, R. Where they meet, they pull on each other, a Newton's third law pair. The right piece pulls the left one way, the left piece pulls the right back, equal in strength, opposite in direction. In symbols, F sub RL equals minus F sub LR. The tension at point P, written T of x sub P, is simply the magnitude of that action-reaction pair, the common size of those two forces. That's the definition. Now, if the rope is massless, each piece has no mass, so the horizontal forces on it must sum to 0, even while accelerating. The left piece feels the block's pull and the tension. The right piece feels the tension and the applied pull. Balancing each gives the same value everywhere. The tension is uniform and equals the applied pull F sub AR. Everything changes when the rope has real mass. Now the rope itself needs force to accelerate, so the tension can no longer be identical at both ends. Here's the classic problem. A block of mass m1 sits on a surface with coefficient of kinetic friction mu k. A uniform rope of mass m2 and length d is tied to it. You pull the far end with a force tilted slightly upward at a small angle phi, just enough to help support the rope's weight. Our goal, find the tension as a function of the distance x from the block. Let's solve it. Because the angle phi is tiny, we treat every force as horizontal. There's a small vertical part holding the rope up, but it barely touches the horizontal motion. The key idea, the rope has mass, so we must account for its inertia. Slice the rope at a distance x from the block. This splits it into two pieces. The right piece has length d minus x, so its mass is m sub 2 over d times d minus x. The left piece has length x, so its mass is m sub 2 over d times x. Now draw a free body diagram for each piece. On the right piece, the applied pull F sub AR drags it forward, and the tension T of x holds it back. Newton's second law gives F sub AR minus T of x equals the right piece's mass times its acceleration, m sub 2 over d. times d minus x times a sub r. On the left piece, the tension T of x pulls it forward, and the block pulls it back with force F sub 1L. So T of x minus F sub 1L equals the left piece's mass times its acceleration, m sub 2 over d, times x times S sub L. We still need F sub 1L, so turn to the block. Vertically, the normal force balances gravity, N equals m1 times g. Horizontally, the rope pulls the block forward with F sub L1, and the kinetic friction resists. That friction is mu k times N, which is mu k times m1 times g. So F sub L1 minus mu k times m1 times g equals m1 times a sub 1. Newton's third law ties block and rope together. The block pulls the rope exactly as hard as the rope pulls the block. So F sub 1L equals F sub L1, which is mu k times m1 times g plus m1 times a sub 1. Substitute that into the left piece equation. It becomes T of x minus the quantity m mu k m1g plus m1a sub 1 equals m sub 2 over d times x times a sub L. Finally, the block and the entire rope move together, so all these accelerations are one and the same. Call it A, collect the terms, and the tension is T of x equals mu k times m1 times g plus in parentheses m1 plus m sub 2s over d times x, close parentheses, times A. Read what it says. The tension at the cut has two jobs: overcome the block's friction and accelerate everything to its left. The block plus the rope behind the cut. Slide the cut toward your hand, x grows, more rope lies to its left, and the tension climbs. So tension is smallest at the block and largest at your hand, where it equals the full applied pull. There's a faster route to the same answer. Instead of cutting the rope, treat the block and the entire rope as a single object. The only outside horizontal forces are your applied pull F sub AR forward, and the friction MK times M1 times G backward. The total mass is M1 plus M2, so Newton's second law reads F sub AR minus MUK M1G equals, in parentheses, M1 plus M2, close parentheses, times A. Solve that for F sub AR. Drop it into the right piece equation from before, and the factor d minus x cancels neatly against the total mass. What's left is exactly T of x equals mu km1g, plus in parentheses, m1 plus m sub 2 over d times x, close parentheses, times A. Two methods, one answer. Always a good sign. So tension is a local quantity. Cut the rope anywhere, and the tension there is the strength of the pull the two halves exert on each other. In a massless rope, those pulls balance out to a single value, so the tension is uniform and equals the force you apply. Give the rope mass and, as long as the load is accelerating, the tension grows steadily along its length, smallest at the block, where the rope only has to drag the block itself, and the largest at your hand, where it must accelerate the block and the whole rope together. Same rope, different tension depending on where you look. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.